In this video, we will talk about Lagrange theorem and Lagrange multiplier, and this topic can be found in 13.10 of your textbook. The one demerit of using the second order partial derivative test in order to categorize critical points as relative extremum is the fourth condition. When the D'Alembert constant small d becomes equal to 0, your test is inconclusive. What you do? One of the solutions for that process is using Lagrange multipliers. In order to understand Lagrange multiplier, we will start with the concept of Lagrange theorem. Even before that, I want to introduce to a general optimization problem and just a general practical world situation. So for example, there is a factory, and this factory wants to maximize the profit, and say the profit is given by a function of x and y. So profit depends on two things, where x is number of workers and y is availability of the raw material. So as number of workers and the availability, both of them, they are boundary conditions. They have limitations. We will say let G is a function that relates these two, raw material availability and the number of workers, and gives you the limitations for them. So we call let Gxy be the boundary condition for this optimization problem. So basically what it does, it tells you you cannot have more than say 1,000 laborers, and you cannot have more than 300 million pounds of such a raw material. So those two, when you express them as in functions, are going to be called boundary conditions. So these type of problems are called optimization problem. When I hear the term maximize or minimize, I call them optimization. So what I need to use Lagrange multiplier? Number one, optimizable function. So you need a function that you are optimizing. The second thing you need is boundary condition. We call this boundary constraint function. When I have the supply of these two theorems, these two functions, I can use Lagrange theorem. Lagrange theorem states if f and g have continuous first order partial derivatives, and you know that f has an extremum at a point x naught comma y naught on the smooth constraint curve gxy equal to c. So first and foremost, we are going to check whether fx, fy, gx, gy, and if it is a three variable function, then you have to include fz and gz, all are continuous. Also, f must have an extremum on this constraint curve on gxy equal to c. If it is three variable, you should say gxy z equal to c. So because this Lagrange theorem is in two variables, let me actually go ahead and take out fz and gz, but you understood what I wanted to say by the concept. Once I have made sure that, then Lagrange theorem tells me if g x naught comma y naught, the gradient of that is not equal to 0, then there exists a real number lambda such that the gradient of fx naught y naught is equal to lambda times the gradient of gx naught y naught. So this theorem is an existential theorem. It doesn't talk about the exact value of lambda, it just says there is a lambda such that gradient of f. What is gradient of f? It is fx I cap plus fy j cap is equal to this lambda constant times gradient of g, which is gx I cap plus gy j cap. And the remark says if you have this Lagrange multiplier condition and your function, instead of being a 2-variable function, now is a function of 3 variables or even more, you can still apply Lagrange theorem and get the supply of this real number lambda. As I said, this theorem is an existential theorem. What I am now interested in is a process, a methodical process of finding the value of lambda, and hence try to solve expressions involving optimizable functions and boundary constraint criteria. So we will go to method for Lagrange multiplier. So what I do, remember first I need to start with similar type of f and g as in the theorem. So my first order partial derivative should not only exist for both f and g, they should be continuous. It must have a minimum or a maximum subject to a constant gxy or gxyz, depending on how many variables you have. Then first you say the gradient of f is equal to the gradient of g times lambda for some lambda, and at this point lambda is unknown. What it will give you, it will give you a system of equation. I will get the first order partial derivatives of both f and g are equal to each other when you multiply lambda to the partial derivative of g. I will get the first order partial derivative of f and g are equal to each other when you multiply lambda to the partial derivative of g with respect to y. And the third equation is going to be the given constant itself, gxy equal to c. Then I solve this system of equation. Solve the system. And it is going to give you bunch of critical points. At each of these critical points, you are going to evaluate your function f, or the function that you are optimizing. The greatest value obtained for a point will be the point of maximum. The least value obtained for a point will be the minimum. If I have more than 2 variables, then I will have one more equation, and that equation is going to be given by the partial derivative with respect to z for f equal to lambda times the partial derivative of g with respect to z. But I still get a system of equation which I solve, and then I check the value of the optimizable function at each of these solutions to understand the maximum and the minimum. In our next video, we will actually work out Lagrange multiplier problems.